This is the Image2Biomass project on Kaggle. It has to do with predicting some biomass components from images and tabular data. We're trying to find dry green, dry dead, dry clover, total dry, dry green, additional matter in grams from these images. Yeah, it's green, dry matter. And right off the bat, you'd think, well, the total dry, that should just be that dry plus that dry plus that dry. And the green dry, that should just be that one. Back when I started this project, I copied a comment down from the discussion board, and the host of the project mentioned that technically, yes, the dry total and green dry matter in the annotations are the sum of the other components. However, predicting these values and then summing them up is likely less accurate than directly predicting the total amount. I am not entirely sure if that would be the way I would do it, but I just left it to be 5 distinct categories for the time being. So downloading the training data set, this is what we get. We get a height format of each individual target value with the image that they're from, and then we get information on each just important types of species in the image. We get the readings, we get everything that we need for prediction. So the first thing we do is we take the comma separated value format and we bring it to a data frame so that we can work with it. I printed the head of it here to show the different categories. And then we're going to print out one image to take a look at it and see how the categories compare. Next, we're going to make the correlation matrix to show the target categories and see how each individual one relates to the other. We can see right away that an increase in dry clover mass relates to less dry green mass, as it's probably taking more area from the grass. Additionally, we can see that an increase in dry green mass is related to more green dry matter and total dry matter, as we would expect. And as dry dead matter increases, we get more total dry matter. These values are to be expected. So here I've got a correlation matrix of the tabular features correlated to the target categories. And we can see that a few of the categories from the tabular data do not have much impact on the target categories. In particularly, we can see that the species doesn't have much impact with light blue values ranging around 0. There are a few species that do matter, but the majority do not, so we're going to remove species from the list. Additionally, we can see that the day number does not appear to matter as much as the height, the readings, and the state. So we're going to actually omit this from the data frame as well, because it will help the model learn more relationships on less data. So next what we're doing is we're taking the categorical features and we're going to do a encoding on that. It's just for the states, and each state will get its own value, so we can pass it into the model for training. Additionally, we're going to take the numeric features from the green readings and the height, and what we're going to do is we're going to normalize those. This table shows what the first 5 rows of the data frame look like after we've rearranged it so that each image has its own row. Also, you can see that we've normalized and we've encoded the values. We do a quick box and whiskers plot to show the distribution of our target categories, and then take a look at the RGB values for the heck of it. The data frame is going to get saved as a pickle file so that we don't need to rerun everything that we've done up until now. So the best way for accomplishing our goal by learning from both the image and from the data associated with the image is to use 2 different models and combine them into one, and this is called a multimodal model. So one half of it is going to be a convolutional neural network, and the other side of it is going to be a multi-layer perceptron. The CNN, that first half, is going to handle the image data, and the MLP, the other half, is going to handle the tabular features. One way to accomplish this is to use intermediate fusion, and that means that the input data will come out not completely formatted into the target categories, and instead will be a certain dimension that will go into another layer, kind of mixed together, and then a dense layer will combine them into the final target values. A good method of maintaining all the running data that we get while training is to make a SQL database. That way we can keep all the information that we need and query for it later. So this method is going to be important. The get best run from database is going to query the database. It's going to make sure that we get the best run from the previous step, and I'll explain steps next. But this will make sure that we keep moving forward while training. The steps are pretty simple. Step 1, we're going to check for the optimal CNN by varying the different model architectures while keeping the MLP frozen. Step 2, we're going to vary the architecture of the MLP while keeping the parameters of the CNN frozen. And step 3, we're going to vary a variety of hyperparameters for the entire model. To feed the model all the information from the pickle file of the data frame, we're going to create some tensors that we will input from each individual row. Each row will give us an image path, and we're going to take that image path to get the image, and then that image is going to be transformed through a few operations into a list of numbers, and that is our tensor input. Additionally, we're going to have our tabular data be inserted just as it is with only a length of 6. The main multimodal model, which combines both the convolutional neural network and the multi-layer perceptron, is stored here in the multimodal model class. I'm using PyTorch Lightning, which helps us create a simplified training procedure. So if you see anything that relates to what PyTorch would usually have, PyTorch Lightning is the method that I'm using to organize everything. So this model, what it's going to do is it's going to take in all of these individual parameters. These are what we're going to be varying during our training process. And it will create 2 individual heads. It's going to create the image head, which will be the CNN, and it's going to create the tabular head, which is going to be based off of the parameters that we've specified to pretty much build a unique architecture for it each individual time that we pass in new parameters. You can see here that the tabular head dimension is 6. Those are the 6 features that we're passing in from the data that is attached to the image, the tabular data, and that will be the input. The output dimension is going to be varied depending on what parameter we decide to represent. So that will be the final multi-layer perceptron feature count. That'll be combined with the final CNN feature count, and those are going to be pushed into the final regression head. That will take the combination of data from each individual model. It's going to reduce it, it's going to condense it, and it's going to make the final prediction, which is our 5 individual target values. Class, we ensure that the training for the multimodal model is going to be completed correctly. We have our training steps, we have the validation steps, and then we have what to do when the epoch ends. We also make sure that we log everything so that we can look at it later, and I log these all in checkpoint files. And then we have our optimizer. This method here is for gathering the model that we'll be using for the convolutional neural network side of our model architecture. It allows us to pick and choose different types of models so that we can compare how they perform in our overall procedure. Checking here that the GPU is going to be optimized for a run. This here is the parameter list that we're going to be tuning. We have the CNN models. 4 of them are being tested to provide a range of capabilities. Then we have the final feature count for the CNNs and the final MLP feature counts. These are going to go into the combination layer for our intermediate step. We have the block count that make up the layer count for the NLP and the amount of neurons. After that, there's the dropout and the learning rates, and then the modality dropout rates, which I'm going to show you now. This is something that I kind of glossed over, but it's very important. The modality dropout is a tactic used in the multimodal trainer class, and it is a value that can be set and varied, but it's pretty much a probability that if a random value between 0 and 1 is generated below, there will be a 0 input put in for the tabular data. And what that does is it allows the model to learn in situations where there is no additional information included with the image. And that's very important because our final test that we're going to have for this project will only include images without the data associated with them. This part has to do with generating the output for the Kaggle competition. The submission is pretty much a collection of the images that we're operating with and the target values that we predicted. And we can make that file by taking the test CSV file. This one looks a lot different than the one that will be available only when we submit, but it gives us a way to practice our run. We'll take the CSV file, we'll look at what images are in it, image directories. It'll go to the test folder, it'll go grab the image, pass it into the model, and then create a prediction for the 5 target categories. There's 800 images for the test file once we submit. So our final submission is going to include the target categories for each of those 800 images. The very last thing we need to do is make sure that the CSV submission file is in the proper format. So that's what this last cell does. Using the log files, we can check how each individual step performed during training. The first 4 runs correspond to step 1, and that was varying the CNN models. See that this first one, the gray one, is ResNet 18. They just go in order of how they're defined in the list. The blue one is ResNet 50, and then the pink one is EfficientNet. The last one did not run, which could do with some error, some scripting error. But for just a quick look at how these three models performed, we can see that the efficient net was on par with the ResNet 50, and the 18 performed better. This could be due to a few different factors. It could be due to the learning rate that we had set. It could be from just general parameters for input and output on the neural net. We really chose a lower number of parameters, and this net is a lot simpler than the 50. The value that we used to determine performance of the runs was RMSE total, and that is the total amongst the 5 target categories. You can see that the ResNet 18 got slightly lower than 20, and that is 20 grams at its cutoff point for RMSE. Okay, I made the graph a little larger so it's easier to see. The next step involved these 9 runs that are highlighted. These runs were varying parameters of the MLP architecture, and they all did relatively well. They were pretty similar, and we can see that the best one just got slightly higher than 20 at 21.5, and that is the total RMSE in grams. So the third graph is a little more confusing. It's a bit difficult to look at right off the bat, but you can recognize some familiar patterns. This decline right here where my cursor is, that's from step 2. We can see that there are some familiar declines from step 1 that made up the varying CNNs. And finally, we get all these remaining runs that are down here below 20. These are all the varied hyperparameters for step 3 of our tuning procedure. And this shows that once we clarified the best CNN and the best MLP, once they began working together while we varied our hyperparameters, the additional ones, in a grid search, it really all came together to lower the total root mean squared error and make our predictions a bit better. So overall, we got the lowest root mean squared error of around 13. Pull it up here. 13.45. So in the end, after submission, this architecture gave me a public score of 0.44, which isn't too bad. It's all right for the first time attempting this. The leaderboards have a score of 0.76 right now. 0 for reference is just random guessing, and I think 1 is completely perfect. So with a complicated data set that has both images and data associated with them, and then you only get the image as input, that is not too bad. There's quite a bit of room for improvement on this project. 0.44 isn't a bad score, but it's also not ideal. 0.44 means that 44% of the variance in the biomass values was a true prediction, but the remaining 56% is just error. There's a few methods that could definitely improve the score, one of them being better models for the convolutional neural network. There's a lot of higher end models out there that could learn more complex relationships that might help improve the proficiency of the model a lot more. There's also a way that the parameters can be tuned so that if a computer with a higher resource capability, higher GPU and whatnot, could just continue running the model, we could train it for much longer, and we could probably get those higher end, more complex models to generate a better relationship between the images, the tabular data, and whatnot. The architecture that we used for the multimodal model could be improved as well. There's so many different parameters in there that could be varied just to find the optimal one. And when I ran this project, there was a total of 45 runs, and that was the 4 varying in step 1, the 9 varying in step 2, and then the remainder were just the hyperparameters in step 3. So there's definitely a lot that could be taken off on from this project. It provides a good baseline, and it gives a good example of how this sort of procedure works. All right, thanks for listening.